Official members bounce, bust off the chrome. Realize it's real hell where we call home.
Official members bounce, bust off the chrome. Realize it's real hell where we call home.
From the heart inside one, I vision fat licks and mat clips. The chroma make the average imitator do backflips. You lack a pistol, so put a vest around the issue. Slugs will never miss you. Coming from members that's official.
All right, so today we're going to continue on the discussion. This will be the last lecture on the storage layer, the bottom layer of the database system. So we're talking about the different ways of representing data, the storage models, and then how to optimize it further through compression. Before we get to that, you have two things came out today. Homework 2 has been released, and that'll be due on Sunday, September 22nd. And that's basically 3 questions, multiple choice, and you'll submit those in Gradescope. And then we've just posted Project 1 is live. The write-up is on the website, and then I think the code and the announcement on Piazza has been released as well. And so there'll be a recitation at 6 p.m. next Wednesday on Project 1. So we advise you to at least get started on it now. Look over the write-up. It's very thorough on what you'll need to do. And that way, when you go to the recitation, it isn't like, what's the buffer pool manager? It's where we like, hey, how do we get started? How do we approach this? What does this class mean? How does this work together? Right? So you want to come up to the recitation with questions about insightful questions because you've already gotten started. Okay? And so the lecture on the buffer pool manager will be Monday's class next week. But it's obvious what it is. We keep alluding to it. It's the thing that moves data pages back and forth between disk and memory. And then I mentioned also last class on Monday and Tuesday next week we're having our visit day from all of the industry partners. So Monday will be research talks. So I'll be there all day, and then we'll come here and have class, and then we'll go back. And then Tuesday morning will be info sessions. And then we just got confirmation right before the class that Confluent will make it. So we're trying to figure out what time that'll be. So some of you asked to meet Confluent. There'll be info session with them as well. Okay? And again, if you're in this class, or if you have friends that have taken 445, 645 before, or 721, everyone's invited to come to this. All right? All right, so last class, we were discussing, again, continuing our discussion on what the storage level or the storage layer of the database system is going to look like. And we were contrasting what we just talked about in the third lecture of this sort of tuple-oriented architecture with slotted pages. And then we said, hey, here's some alternative approaches to actually storing data. The log structured approach, where you're just appending all the changes and deletes, and then it make the writes go faster, but the reads go slower. And then index organized storage was basically saying, instead of having this heap file where things are unordered, we're actually going to use an ordered data structure, typically a B+ tree, and just have the leaf nodes be the data itself. So all of these approaches that from the last 2 lectures, these are going to be useful for workloads that are write heavy. You do not insert, update, deletes, or upserts, right? You're making a lot of changes to the database, and you want that to work as efficiently as possible. But then there's this whole other workload that you kind of did in homework 1, where it was read-only queries, because you're basically running analytical operations or analytical queries to try to derive new information from the existing data that you have. And in those kind of queries, we don't care about making the inserts, updates, and deletes as fast as possible. We care about making the select queries run as fast as possible. So that's what today is about. Today is about understanding how can we store data in such a way that will make selects go faster than we could otherwise in the slotted pages or the LSMs or the index storage. So first, understand what it means to make analytical queries go faster. We're going to spend a little time to quickly discuss. Here's sort of the rough category of what database workloads look like, and put it into terms so that when we use those terms later in the semester, you'll know what I mean. Then we'll talk about the storage models, and again, this is the way to represent tuples. And then we'll see from the column store approach how we can rely on compression to speed things up further, make things smaller. And then we'll finish up again with a talk from StarTree, which is going to be a analytical database system that's going to use the column store stuff that we're talking about in this lecture. Okay? So a very loose categorization of database workloads can be roughly described in these 3 terms. The first is called OLTP, or online transaction processing. And this will be workloads or applications that want to ingest new information from the outside world. If you're a new startup, this is typically what you end up building first. Like you build a website to take, people put stuff in and you want to store it in the database, right? Those are running update, insert, update, delete queries that are taking changes from the outside world, and you want to store it in your database. So these are going to be typically more write-heavy than the other ones we'll see in a second. But the thing to note about is that the queries that we're going to run in an OLTP workload are going to be, they're not going to touch a lot of data at a time. So what I mean by that is, if you ever think like when you go on Reddit or Hacker News or you buy something on Amazon, right? You fill out some forms, you click some buttons, and it records those changes. The amount of data it's actually storing when you do those operations is pretty small, right? When I buy something on Amazon, I put things in my cart. It's inserting a record in some cart table somewhere. And then I make a purchase, it updates my payment information, updates its delivery information, right? I'm inserting a small amount of data to do, to make that purchase. Now the entire Amazon database is massive, right? Because it's everything anyone's ever bought since the beginning, since the beginning of time. And so that database itself is going to be huge, but the amount of data I'm inserting or changing is quite small. And that's typical in OLTP. So contrast this now with OLAP, OLAP, or online analytical processing. This is where we have an existing data set. We have an existing database, and we want to extrapolate new information from it. Right? I said before, this is what data scientists are typically doing. Right? You're trying to derive new things or new patterns or information that you didn't have before from the data you've already collected from the OLTP system. So these queries are typically going to be more complex than you do in the OLTP systems. Right? OLTP systems like go get Andy's account, right? It's select star from account where username equals Andy. Right? The query is quite simple. But analytical could be something like compute the most find the item that the customers have bought the most when it's a day in September in this city at this temperature at this time of day, and they have other sort of features and characteristics about that we want to break it down on. Right? And typically, you'll be joining a bunch of other tables when you run these queries. And then the last one is sort of a marketing term, although OLAP was as well, but it's in the vernacular now, so people don't remember how it came about. But this is a Gartner term from a few years ago. It's basically saying that there's some workloads where you want to do some OLTP and you want to do some OLAP at the same time, and can you design a system that can try to accommodate both? In actuality, most applications are going to look like this anyway. Right? Like you'll do some OLTP stuff, then maybe there's some queries that would extract new information. But there's a couple of systems that claim they're an HTAP system because they want to try to do both things at the same time. So if you sort of think about the workloads on these two axes, first the x-axis here is it write heavy versus read heavy, and then are the queries of the operations going to be simple or complex? You can think of like a quad chart like this where OLTP is down in this corner. We're going to be doing not always write-heavy workloads, but more write-heavy than OLAP. So we do much more inserts, updates, and deletes. But the queries we're going to be executing are going to be simple. And they're only going to touch a small amount of data. And then OLAP would be in this other quadrant up here, where the queries are going to be more complex than OLTP, but they're mostly going to be read-only. And so the reason why I was saying that this OLAP term was a marketing term in the 90s, so most databases up until the late 90s, we're just, OLTP was a category, but everything was basically OLTP. Because most businesses, most people that are running databases, you just needed to collect information. And only later on did people start wanting to do more complex analytics on it. So in the 90s, there was this guy named Jim Gray, a very famous database researcher. He invented two-phase locking and a bunch of other stuff. We'll cover the rest of the semester. He won the Turing Award in databases in 96. Well, he wrote this paper in like 93, 94, where he's like, hey, here's this new category of workload. It's called online analytical processing. It's called OLAP. But then it turned out he was being paid by a company that was trying to brand OLAP system, so he had to retract it. But the name still stuck. And then HTAP will be sort of here in the middle, right? But if you tell somebody I'm running an OLTP system, they'll roughly know what you mean. If you say you're running OLAP system, they'll roughly know what you mean nowadays. So to delve deeper now into what these workloads will look like and how storage can affect them, let's use a really simple database schema. Sorry, yes?
So how do you measure the complexity of a query?
This question is, how do you measure the complexity of a query? In terms of think of the number of joins. How many tables am I accessing? How many aggregates I'm doing? There's no scientific measurement. But like select star where name equals Andy, that's pretty simple. But select star where name equals Andy and join in this and join, and so forth, and do an aggregation and a window function and CTE, that would be more complex.
Okay.
Yep. Yes, in the back.
In the previous slide, what of the other two quadrants?
The question is, what are these other quadrants? Like, what would be a write-heavy complex workload? And this is not exact. It's not exact science. The lines are blurry. So you might have a more complex. You could have a. I don't really bring up transactions, but you can imagine other that I can be write-heavy, but doing complex transactions. Like I want to update 1 billion records in a transactionally safe manner. Just read-heavy, read-only complex queries overlap. Doing a bunch of writes on small amount of data, simple queries, OLTP. Like that dichotomy is enough to understand what two systems you would want to choose. All right, so this sample database schema we're going to use is actually derived from Wikipedia. Like Wikipedia, as far as I know, is still written in PHP. It runs off MySQL, a massive MySQL cluster. So you can go, it's open source, you can just go download their MySQL files and see what the schema looks like. This is a rough approximation of it. So I have 3 tables. I have user accounts, pages, and revisions. And revisions has a foreign key reference to the user ID that made the revision, and the foreign key reference to the page that it corresponds to. And to speed things up, the page table actually has a foreign key reference back to the revision, which is going to be the latest one. So if I'm trying to look up the latest version of a page, I just follow that foreign key, right? So just remind us again, the relational model doesn't specify anything about how we have to store data in a table, or the tuples, right? And there's nothing about the relational model that says we have to store the data for a single tuple all within the same page, right? We saw that last class when we talked about overflow pages. If I have a really large varchar, I could store that in a separate page and just have a pointer to it, right? But again, as I said at the end of last class, when you think of a database, you probably think of like an Excel spreadsheet where like all the values for a single row are contiguous, one after another. And the problem is going to be if we build a system based on that assumption, it's not going to be the most efficient for some of the workloads, in particular for the overlap workloads. So if you take the Wikipedia schema and you want to run simple OLTP queries on it, it would sort of look like this, right? So if I want to get the latest page the latest revision for a page, I'm just doing a simple join on page and revisions and following that revision foreign key to get the latest one. So it's like doing a single tuple lookup on the pages and a single tuple lookup on revisions. And we can execute that join pretty efficiently. We'll cover that later. Or if I'm going to do an update query, this is keeping track of the last timestamp of when somebody logged into a given account. Or if I need to insert a new revision, right, it's just inserting to the table with all the values. For overlap, it would look something like a more complex overlap query would look something like this. So I'm only doing a single scan on user account, but now I need to do an aggregation on to find when somebody logged in with the host name that ends with .gov. This is actually a real example from a scandal a few years ago where, because all of the revision history in Wikipedia is public, they found that there was like, for people in Congress, their admins or staff were actually going and updating the Wikipedia records, logging in on government computers, and you would see the .gov host names. And so that's obviously illegal. You can't do that. So this query would help you find these things, right? So in this case here, even though, again, I'm only scanning one table, but I'm scanning just basically, I need to access 2 columns, the host name and the last login, but I need to see all of the tuples in order to find the ones that end with .gov, and then group them by the month that they logged in, right? So a database system storage model is going to specify how we're going to physically organize tuples on disk and in memory. And as I said before, depending on how we do it, like a row store versus a column store, that's going to have a significant difference in performance based on what workload we want to run. So the canonical approach most people think about when they think about database storage will be called the n-area storage model, or NSM. It's sort of the academic term. If you said row store, it's the same thing. Decomposition storage model, or DSM, or column store would be the more common term. It's another approach. And then we'll cover this last one called hybrid, or PAX, which is going to look a little bit like the NSM, look a little like DSM, and still get the benefits of both of them. So, as I already said, the NSM, or the N-area storage model, is where you store almost all the attributes, all the values for a tuple are just contiguous with each other in the same page, right? And this is going to be great for OLTP, as I said before, because most of the time on OLTP workloads, I'm accessing a small number of tuples, like typically one, like if I'm doing a primary key lookup, and I'm typically going to need all the attributes for that, in that query for that tuple, right? A select star query from table where username equals Andy, the star is obviously getting all the attributes. So I want all of all the values for that tuple returned back to the client. So if they're contiguous with each other, then I just jump to one page, ignoring overflows, jump to the offset in that page based on the slot array or however I'm storing it, and just do a mem copy and get all that data out that are right next to each other, right? I don't need to jump around to different locations in memory. And as we said before, the database page sizes are typically going to be some constant of the hardware size. And so again, if everything fits in a single page, it's one read to go get the data that I need, right, for most of these queries. So this is just a reiterating what we talked about before. Again, what the storage is going to look like. Again, we're assuming we're doing tuple-oriented storage with slotted page, with slot arrays. And so we just have this header with these slot arrays. And then as we scan through and add our data, we're just appending it to the end. And now I'm showing that every record is going to have some header in front of it. Right? This is where you would store the null bitmap that says what attributes are null or not. And so as I scan down and just insert all this data in from this table, right, I'm just filling it up one after another and just adding pointers in the slot array. So again, if I want to go select star from where username equals Andy, I have some data structure that gets me to this page, and then I jump to some offset and then just read all the bits that come after that. And that's going to be all the data that I need. And I don't need to jump anywhere else. So we go back and do a simple query on our Wikipedia database, right? Select star from user account where username equals Andy or whatever, and then check the password. Ignoring how I find the record I want based on the username, right? We'll cover that in 2 weeks or next week in lectures 8 and 9. Right? There's some index data structure that's going to give me a record ID for a given username. And then now with that record ID, I go to the page directory. It tells me what page my data is in. I then look in the header, find the slot offset, find the slot entry that has the offset I want. I jump there, mem copy everything out, and I'm done. All right? If I want to do an insert, again, that's easy to do. Look at my page directory. It tells me where a page has empty slot. And then I just jump to that offset and just write all my bits out. Right? This is easy. Or this is perfect for a row store. But if I run now my analytical query on this, now you see why this is going to be problematic. So in this case here, my where clause says where hostname like wildcard.gov. So assuming I don't have an index on this, I got to look at all the host names to find find the ones that match my like clause. So I'm going to scan all the pages in this table. So assuming I bring this first page in, right? Now I want to start running the parts of the query. Well, I have, again, the where clause on host name. So what do I need to do? I need to scan through the slot array, find all the offsets for the tuples that are in the page, jump to each offset, then jump to the offset within that tuple of where the host name starts, then evaluate my predicate, my where clause, then jump to the next one and repeat it. And that's just for the where clause. Now for all the tuples that match, I want to run my aggregate. So now I need to look at the last login entry and compute, extract out the month and compute an aggregation on that. Ignore how we'll compute the aggregation. That's in a few weeks. But let's assume there's a hash table I'm maintaining in memory that I'm updating this counter. Right? It's pretty simple. Right? But now what do I need to access? I need to access all of these attributes over here. Now I can do this while I'm accessing the host name. Like I'll check the host name. If it matches, then I'll do the aggregation portion, so I don't have to loop back a second time. But I'm still I'm still going through each tuple one by one and jumping to these offsets. So what's the big problem with this approach for this query? I got this big block of data here for these 3 attributes, and I didn't need them for this query. But because all the attributes in n-area storage are packed together, all the values for a tuple are packed together, they come along for the ride when I go fetch this page. Right? Because again, it's block-oriented storage. I got to go get the entire database page, bring it in memory. Even though there's a bunch of data in it, I don't actually need for this query. So this is one of the key problems that we're going to have with a row store when we run analytics, because it's going to be all this useless I/O. So NSM, the row store, the advantage is going to be it's really great for inserts, updates, and deletes. Anytime I'm updating a small amount of data, this is fantastic because it's going to be one page, right, and I'm done. It's great for queries that need to get the entire tuple. Any select star query, which you shouldn't write anyway, but like there's a lot of them. Then all my data will be right together. And then we can use other techniques like index ordering and storage to keep everything in sorted order, so the physical layout of the data is actually good for queries as well. But as I showed, that it's going to be bad for scanning large portions of a table, especially when I only need a subset of the attributes. Right? If I have to look at all the attributes in all the data, for all the attributes for all the tuples, column store will help for certain things, but at the end of the day, you got to read everything. So, but if most of the queries are going to be a subset. As we showed before, I'm jumping around to different offsets in memory, and that's going to suck from a CPU perspective because now you have a bunch of branching, and in direction, that's going to make things slower. And then what we'll cover later in this class will be we're not going to be able to compress this data very well because we have a bunch of attributes with different value domains that are all being intermixed, and that's not going to be ideal for a compression scheme. I'll explain what that is in a second. So any questions so far, like why row stores are bad for analytics? Right, it's pretty obvious once you see it. So the alternative is going to be the decomposition storage model, or DSM. And this is what you would, DSM is the sort of academic term, but everyone just refers to these as column stores. And there is a exact DSM definition, and most column stores are going to be using the PAX model, which we'll cover in a second. But they're loosely, at a high level, they're basically the same. So the DSM is basically, instead of storing all the attributes together for a given tuple, contiguously in a page, we're going to store all the values for all tuples for one attribute contiguously in a page. Right? So instead of having the host name followed by the last login, I'll store all the host names for all the tuples together contiguously, and then have another set of pages that store all the last login attributes for all the tuples together in a page. So again, the relational model gives us that logical and physical data independence, where logically I'm defining a table as a bunch of attributes and columns, but I'm not specifying how I'm physically storing it. So the database system, if it's a column store, can say, OK, well, I'm a column store system. You told me their table wants to be, has these columns, but I'm going to split them up and store them in separate locations. And then when your query comes back and says, give me all those attributes back, I'm going to stitch the tuple back together to make it look as if it was always stored together. Right? And we hide that entirely from the application. So if we go back to our simple example here, for the first column on column A, that'll just be stored in a separate page or set of pages, all the values for column A. Right? And there'll be a header that says, here's what column A, here's what's in this page, here's some checksums or whatever else you want to store. There'll be a null bitmap that's stored at the header as well. That's for all the tuples, for all the values for all the tuples. So instead of having a separate bitmap header per tuple, now it's on a per column basis. But I know what offset in my bitmap corresponds to what offset in value and what tuple that corresponds to, what logical tuple that corresponds to. And then I have the same thing for the other two columns here. And again, I'm showing these as one page, but you can imagine this could be multiple pages. So if I go back to our query before, so this is what our original page looked like under the row store model. Right? We had a bunch of tuples, we had a header at the beginning of the tuple, and then we had all the attributes. And then once we had to get the last attribute, then the next tuple starts. So now what I'm going to do is split this up based on columns and store these now all in separate pages. Right? So there'll be a user ID page or pages, a username, last login, and so forth. And then here I have the hostname page. And again, we have a header, tells me some metadata about what's in this page, what column it corresponds to, some checksum information or compression information, and then I just have all the hostname values. So now when I run that same query we had before, the first step is to evaluate the where clause. And so the where clause is only accessing the host name. So I only need to access this one page. Again, assuming everything fits in one page. I go access this host name. I start at the beginning, and now I just rip through this and apply my where clause to find the thing that I'm looking for. So what you're going to end up with now is a bunch of matching offsets. Right? So saying here's the tuples that where the value evaluated true for this predicate. So I keep track of those offsets, which we'll cover in a few weeks. And then now when I want to then evaluate the aggregation, I just bring in the last login page, because that's the only column I need. And then now I know where the offsets were from that match to the host name. I know those are the last logins I want to consider in my aggregation. So again, so this simple example where there's only 6 pages in the database, I went from, in a row store, having to read all the pages to now only having to read 2 of them, or a third of it. And if you assume that, again, always think in really large scales, like I have billions of pages or petabytes of data, and either the disk is really slow and it takes a long time, or I'm paying for the access to disk. Like if you're running in the cloud, you pay Amazon every time you look something up in S3, then this is a huge win. So not only do my queries run faster, they're going to run cheaper as well. So is this clear? So this seems like a no-brainer idea now. And actually, who here has heard of column storage before this class? Less than, okay, barely 5%, 10%, right? This seems obvious though, right? Like, of course, if you're doing analytics, you want to store it like this. The idea is actually really old. It goes back to the 1970s, but it was in this obscure Swedish military tech report for like a file system, for this system called Cantor that nobody paid attention to. And then that DSM paper I showed you before, that came out in like 1984. And it wasn't really until like the 2000s when people said, oh yeah, this is actually a really good idea. We should store analytical data as column stores. So it took a while for this idea to come along, and now it's commonplace and it's used everywhere. Right? Because again, the wins are so big. All right, so I was kind of hand wavy back here, right? When I said we run our where clause, we find our matches, and then now when we bring in the last login, we have a way to know where the corresponding matches are in the host name to match the corresponding matches or the values that we care about in the last login page. So how are we doing that? So there's basically 2 approaches. One is that we just use fixed length offsets for all the values within a column, and we just know that logically the tuple tuple 1 is at offset 1 at each of these columns. And because the values within each column will always be fixed length, like there'll always be 32-bit integers or 64-bit integers or whatever, then we know how to do that simple arithmetic to go find the offset that we want to get the value we need for a given tuple we care about. This is the most common approach, and pretty much everyone does this. In the early days of column storage, about the mid-2000s, it was still kind of up in the air how to do this. And the alternative approach was basically to store a tuple ID with every single value within a column, and then have some additional data structure that says if you want attribute, or sorry, if you want tuple 1, here's how to jump it into that offset in the different columns of different types. Right? There was a system, I want to say it was Data Allegro, which was bought by Microsoft, that was basically contorting a row store system to make it look like a column store like this. Microsoft paid, I'm pretty sure it was Data Allegro that did this. But even so, when Microsoft paid $200 million for Data Allegro, within 3 months they realized the code was garbage and they threw it all away. And that was actually Jignesh's advisor told him to do that. Anyway, so I can put this marker up here. Don't do this, right? But I wanted to tell you that you could do it this way. This is going to be the most common approach, using fixed length offsets.
So how do you handle very low length?
This question is, how do you handle very length? Next slide. Yes, absolutely. Yes. All right. So integers, floats, dates, they're all fixed length. That's fine. How do you handle the varchars, the texts, and the blobs, right? So the way you basically do this is that you want to convert everything into fixed length. And the way we're going to do that for varchars is to use basically dictionary encoding. All right? If you're very familiar with the compression algorithms, they're basically doing some variant of dictionary encoding. You're taking an arbitrary string And instead of storing that string in the column, you're going to store a number, an integer, a dictionary code that maps to that string. So I have a separate data structure that keeps all my strings and the mapping from codes to the actual original values. And then in my columns, I'm just going to store the integers. And now everything's fixed length, and we're all happy. And in some file formats, like I always get this wrong. There's Parquet and Oracle, we'll talk about in a second. One of them does dictionary encoding for everything, no matter what the data actually is. So everything ends up being 32-bit integers in the columns, or 64-bit integers. And then one of them only does it for the strings. Right? So that solves that problem, because now we just do the simple arithmetic, and because we know it's going to be 32-bit integer codes, we just jump to whatever offset we want to find the data we need. We'll cover that more in a second. All right, so in the DSM, the column store, it reduces the amount of I/O for queries and only need access to a subset of the attributes of a table, because we're only reading the data we actually need. We're not bringing in things because it comes along for the ride. We're only reading exactly what we want. It's also going to let us execute queries more faster, is because we're not jumping around to different offsets in memory. We basically can access strides of memory sequentially, and that's the best thing for a modern superscalar CPU. Right? The Intel x86 wants you to execute a bunch of instructions one after another and not have branching, not have jumps. So I can, if I build my system correctly, which we'll cover in a second, or cover it in a few weeks, I can rip through that column store and not have any indirections or branches, because I'm just going through exactly like value after value after value and doing the same operation, running the same where clause over and over again. And that's the best thing for modern CPUs. And then we'll talk about it later in this lecture. We can get better compression, because now the value domain for a bunch of data that's contiguous in a column store is all going to be the same. It's going to be all a bunch of zip codes that are going to be integers, and I can compress those very, very well. Yes?
Does data compression breaks the offsets?
His question is, does data compression break the offsets? You mean if you run like gzip or zip or snappy? When you say compression, what do you mean? Well, we're going to cover this in a second, but like it'll make it clear. Like, so if you just take like Snappy or gzip or whatever your favorite compression algorithm off the shelf, yeah, absolutely. We're not going to do that. We're the database. We do it ourselves. Okay, we'll come back to that. All right, what's the obvious downside of this? Well, again, if my reads are going faster, what's going to get slower? Any update operations, any writes, because now I have to take, for an insert that shows up, I got to then split it up in a bunch of attributes and write it off to a bunch of different locations. So if I have 1,000 attributes in my table, I got to write out 1,000 pages for just inserting one tuple. That sucks. So PAX will solve that problem a little bit. But in some systems, what they actually do is that they'll have basically what looks like a log-structured system as a write buffer that you do all your insert ups and deletes into, and that's basically a row store. Then in the background, instead of compacting it like we talked about before, where you're making SS tables and so forth, the compaction part is really installing it into the column store, and you do that in the background. Right? Some systems like Oracle, they'll have the row store that you normally would have in regular Oracle that does all your OTP as a row store really fast, and then they actually make a separate copy of the database in memory that's actually in a column store. So when a query shows up, they say, oh, you want to do analytics, and the data you want is actually in the in-memory column store. I'll route your query to that. And so you don't change any of the application. You don't say, I want to go to the row store or the column store. The database system figures that out for you and hides it underneath the covers. And you get all the benefits of a column store, but still have fast OLTP. All right, so there's a bunch of different ways to introduce the idea of column stores into a database system. Some systems are dedicated entirely to be a column store. Some systems have it as a sort of supplemental storage or additional storage. Okay. So column stores are great. The sort of pure column store is great if you only access, say, one column. But that is pretty rare. Most of the times you want to access a couple columns. Maybe not all of the columns, right? I think Postgres lets you have 16,000 columns per table. It's a hard-coded limit in the code. Oracle famously has a 1,000 column limit. The reason was because it used to be 100, because somebody hard-coded that in the 90s, and in the early 2000s, somebody said, well, that's dumb. Let's make it bigger. So they changed it to 1,000, and they had mainly changed a code. And it was such a pain that they told me they never want to change it again. You think they would have made it something bigger than 1,000 when they did all the retrofitting, but they didn't know why the person did it that way. Anyway, so most of the queries are going to access some subset of the columns. And so if now we're a pure column store where everything's in completely separate pages, then yes, we're going to have to go fetch all those pages that we need and bring them in. So what we really want is, as I said, almost a hybrid approach where we are getting the benefits of a column store where things are now, the attributes for a column are sort of contiguously across for multiple tuples, but they're still physically close to each other such that I can bring pages in and yes, maybe getting some data that I don't actually need, but it's not as bad as a pure row store. So this is what the PAX model does. PAX stands for partitioned attributes across. This was the paper claims, or the author of this paper used to be the database professor at CMU before I started. When she left, went to EPFL. The reason I'm here is because she left and went to Switzerland. She's brilliant. But this was the last chapter of her PhD thesis at Wisconsin. And her PhD advisor was also Jignesh's PhD advisor. But this basic idea here is that we're going to have, instead of within a sort of a table, we'll have these sort of mini blocks or larger blocks. I don't use the term block. They're called row groups, or larger regions of data, where within that we'll store things as columns, but the data within for a single tuple will still be relatively close to each other. This make more sense in a second. Right, the idea is that we want to get the benefit of a column store, but still get the benefit of spatial locality, that the data for a single tuple is close to each other. And so, when I was saying before, most systems, when they say they're a column store, they're really going to be doing this. Or if you use these open source file formats like Parquet, Orc, and Arrow, they're going to be doing PAX. And sometimes you'll see it in their literature that they refer to it as PAX. So what we're going to do is we're going to horizontally partition the tuples into row groups. I think Parquet calls them row groups, Orc calls them something else, but it's basically some number of tuples. And then within the tuples in the row group, now we're going to vertically partition them into column chunks. So let's say we have a PAX file here, and this is modeled off of something like Parquet and Orc. And so important thing to understand that Parquet and Orc are read-only file or immutable file formats, meaning like I write it once and I never go back and update it. So the way it works is that there isn't a header for the metadata. It's always going to be in the footer. Because as I'm creating all my row groups to fill up the file, I keep track of what I'm putting into it. And then when the file is done, when you finish it off, you put all the things you've collected into the footer. So if you want to open up one of these files, you look in the footer first, and that tells you what's going to be up above. Right? Whereas like in Postgres and other systems we talked about, it's always going to be in the header because they're dynamically updating these things. All right, so we now take the first three tuples in this table, and we're going to combine them to be in our row group. And every row group is going to have metadata, like the header from the page, so it's going to tell us what's in it. And then within this row group, we're going to write out all the data for the first column, and then we're done. Then write out all the data for the second column, and then so forth to be all the tuples. All right. Or sorry, all the columns. And then we're done. And then now we're just going to do the same kind of partitioning for the next three tuples, and that's going to be stored as a separate row group. So the row group size is going to be different than what we typically think about in some multiple of 4K, 8K, like the pages we saw before. Right? Again, these are immutable files that are going to be used for analytics. So the row group is going to be quite large. I think the default in Parquet is 128 megabytes. Orc is going to be 1 million tuples, no matter what the size is. It's always 1 million tuples. Right? But the idea is that if I'm going out to S3 and getting a row group, I can do 8 megabyte chunk reads from S3, and I get this whole thing, and then all the data that I need for any one tuple is going to be there. So you can actually see there's a presentation from Databricks, the internal organization of a Parquet file, and again, there's the row groups, there's column chunks, and then there's the pages themselves. And the default can be 1 megabyte pages, because again, you're doing analytics. You don't want to read single pages at a time, that's 4 kilobytes or 8 kilobytes. You want to read large strides of data, because you want to bring those into memory and rip through them. Okay? So again, it's like the PAX is basically saying I have some data that's it's as a column store, but the values for the same tuple are going to be close to each other. And you can say, oh, well, is 120 megabytes, are you close? I mean, in modern systems, yes. It's not going to fit in L3. Actually, that's not true anymore. I mean, AMD will sell you a CPU that has like 800 megabytes of L3 cache, which is insane. But like still, it's much bigger than 4 to 8 kilobytes. All right, so if we say that I/O is the main bottleneck in a database system when we have to read data from disk, whether it's a local disk or S3, then we need a way to, and column store is going to allow us to reduce the amount of useless I/O that we're doing. Right, so we've already, say we're a pure column store, we've already got it down to be just bringing in, fetching from disk, the bare minimum we need to actually execute the query. So how can we make this thing go faster if we're already retrieving the minimum amount of data we need? Well, what we want to do now is for the data we do have to read from disk, let's increase the amount of useful information or number of tuples we're getting from any I/O that we're incurring. And this is where compression is going to help us. So think of like if an uncompressed page, I can read 10 tuples. A compressed page will allow me to read 20 tuples inside of it. And the classic trade-off is going to be compute versus storage, or compute or speed versus compression ratio. Right? I can have a very, very aggressive compression scheme, and that's going to be reduce the storage size quite a lot. But now when I want to go read the data to execute my query, I got to unpack it, and that's going to be really expensive. Right? Think of like a modern video codec. They get great compression ratios. They get really small file sizes, and you can barely notice the difference. But it requires modern hardware to decode them, versus like MP3s from the 1990s, right? That's pretty simple now. So we're willing to make the trade-off in some cases, depending on our environment and our workload, that yes, we'll pay a higher CPU cost to execute queries, but that's offset by the reduction of reading less data from physically in disk, right? And in some cases, we'll see that we actually can operate directly on compressed data without having to decompress it. And again, it's why we want the data system to do all this for us. So we have 3 goals for the compression scheme in our data system. The first one is the question he brought up is, well, if I'm saying in order to have these fixed length offsets in my columns to be able to jump to tuples very quickly, if I start bringing in compression, doesn't that break all that? Well, again, if you're using off-the-shelf compression scheme, yes, but we're going to implement compression ourselves inside the system. In some cases, we actually want to postpone or delay actually decompressing data for as long as possible as we execute queries. Right? If I have a billion tuples that's all compressed, and I'm doing a lookup and I want to find one tuple, right? There's it's like a needle in a haystack problem. I want to be able to rip through that a billion tuples, keeping it compressed, find the one thing that I want, then decompress that one tuple, versus like decompressing the 1 billion tuples just to find the one thing. All right, this technique is going to be known as late materialization. We can do this for other things, like if it's a column store, we don't want to have to go stitch the tuple together at the very beginning. If we know that we can throw away a lot of data, so we'll keep everything, process that one column and only get the other columns until later up in the query plan. We'll cover that more in a few weeks, but the idea is, again, just you want to delay as much as possible doing useless work, or avoid doing unnecessary work. And the last one is that it should be obvious that we want to be doing what is called a lossless compression scheme. What does that mean in the context of databases? You don't lose data. Right, so if I compress data and then I decompress it, I should get the exact same data, exact same bits. Right? And the reason why, obviously, that you don't want to use a lossless scheme, something like MP3 or MP4, where you are taking advantage of how humans perceive music and videos, where you can throw away a bunch of bits for things you don't need about because humans aren't going to detect it. When it comes to data in a database, people will notice if the bank account has the wrong number or money goes missing, right? So we don't want to be doing a lossy scheme. Any lossy compression you want to do has to be done by or controlled by a human. So think of like if I have an application that's storing the temperature in this room every second. And so I let this application run for a year. So I have a year's worth of data of what the temperature is for this room at 1 second granularity. Am I really going to care about maybe, again, that exact 1 second granularity for a year from now what the temperature is right now? No, maybe I could aggregate it together into 1 minute or 10-minute chunks. So I have the rough average of what the temperature was within 10 minutes, but I don't have exact values anymore. That's an example of a lossy scheme. And that's not something you want databases will do it for you if you ask them, but it's not something they'll just do automatically. All right, so there's different granularities of what we can compress. We're going to focus on the first one and the last one. These two they exist, but they're less common. Like attribute level compression would be like if I have an overflow page in Postgres, I can compress the overflow page for that one value with that single attribute. But like for what we're talking about today, that kind of stuff we're not going to. You can't really do anything specialized with that. So we're going to talk about block level compression and column level compression, and we'll use block level compression as the straw man to see. Again, not to pick on you, but like to bring up his example of what you can do with this, and then why it's not going to allow us to do everything, achieve all the goals we showed in the last slide of doing late materialization and trying to keep things compressed as long as possible. Whereas the column level compression will be implemented by the database system, and we'll get the best performance for it. So I'll say also too, block level compression will be more common in OLTP systems and row stores, and we'll see how MySQL does it in a second. Tuple level compression can be done in SQL Server, and then there was a system called Terark, which was a fork of RocksDB that the TikTok people bought. What's TikTok? ByteDance. Yeah, so ByteDance bought that company, but they could do tuple level compression for LSMs. For attribute level compression, we talked about Postgres in the Toast stuff, but pretty much every column store system, every system that's doing PAX is going to be doing some type of column level compression. And like the Parquet and ORC file formats give you that. So let's look at a naive compression scheme based on blocks. And so it's pretty easy. We have a block, we have a page, we want to write out the disk. We'll just run it through your favorite compression algorithm before we write it out. So it sits on disk in compressed form. You can use LZO, LZ4. The Snappy is a modern variant from Google based on LZ4. Z-standard is what's considered the state of the art now from Facebook. I think it's from the same guy that wrote XXHash. But this is, if you're using a compression scheme, you want to use Z-standard. It's considered the best right now. And it's the best trade-off between performance and compression ratio. And then Oracle has their own proprietary thing, which I think they still use, called OZIP, because they patent everything. So again, trade-offs are just like before. We're going to care about what's the cost of decompressing and compressing, and then what's the overhead of the storage space. But we also need to care about now when we actually decompress things, and how does that fit into our buffer pool? Because as he was saying, now our pages might be different sizes and not going to fit easily into that scheme we talked about before, where everything has to be always the same page size. This is how MySQL does it. So you have a compressed page. It's going to be of 4 possible sizes, either 1, 2, 4, 8 kilobytes. And if you're less than whatever the next one up, they just pad it out. So if you're like 3.8 kilobytes, they'll pad you out with a bunch of zeros to make you be 4 kilobytes. And that allows them to use fixed length offsets to jump to the different pages that you need. And then they're also going to have this mod log space at the header of the page that they can use to absorb writes without having to decompress things. So again, this idea of log structured storage is showing up in a bunch of different places, and this is another example of it. It's basically that log structure thing we talked about before, where here's all the puts and deletes that I've made to things that are in the page. So now if I have a read query that comes along and wants to access this page, say we do a write query. So I want to write to this page. If it's say an insert, then I can just put the entry into the mod log without decompressing it and then doing the insert. Right? If it's a read followed by a write, if I'm updating someone's bank account, adding 1 to it, then I got to go read it, decompress it, and then do the update. But if it's a blind write, I can just do the update directly to it. And then now if someone comes along and wants to read it, if the read can be handled by the mod log, like if I insert tuple foo and then someone looks and wants to read tuple foo, if I can find the answer I want in my mod log, I keep it compressed. But if I need to access something that's not in the mod log, or I have to derive something that can't be computed from the mod log, then I have to decompress it. And then now it'll expand out into the standard 16 kilobyte page that MySQL has. And then at that point, they're basically almost replaying the mod log and applying the changes into the page. So that when it gets written out, we'll compress it back up, the mod log becomes empty, and then I write it back out to disk in that form. All right? Is this a good idea or a bad idea? Raise your hand if you think it's a good idea. Nobody. Raise your hand if you think it's a bad idea. Why?
What if it's write heavy?
He says, what if it's write heavy? Well, what are your writes? A bunch of inserts?
Yep.
Yeah.
The mod log will be full, and we have to constantly push modified logs into the compressed page.
Right. So he says if it's a bunch of inserts, then you're going to keep just appending to the mod log and it explodes up, right? But you could be clever about it and say, okay, well, when I create a new page, it's going to be uncompressed. So I'll just insert into the page as it was before, and I don't pay the overhead of updating the mod log. I don't know what MySQL does, but they might be doing that. Anybody else why it's a bad idea? I actually think it's a good idea, right? My Postgres can't do this, right? My disk size is smaller. The data I'm fetching in is now smaller. I'm getting more bang for the buck. I'm getting more tuples for every I/O that I'm doing, right? This is a good idea. Again, there's extreme cases where if it's read file by write or write file by read, like where I'm just compressing, decompressing it over again. Yeah, that'll suck. But in general, most workloads are going to be read heavy, even in row store. And if I can answer them using compressed data, then fantastic. And again, there'll be some metadata in the header that says like how many tuples are active inside this. So if I just want to do a select count star of getting the number of tuples in a table, I can in theory just read that out from the header and not have to decompress it. So it's not great though, obviously for doing the late materialization we want to do, because in order to read anything inside it, I always have to decompress it potentially, right? And the compression ratio is not going to be that great either, because it's a row store, so all the values within it are going to be from different domains, right? There's different attributes, zip codes, phone numbers, email addresses, right? The compression algorithms that really, the best case for a compression algorithm is like a bunch of zeros, right? Because it says, all right, I have a zero followed by 10, a billion times, that you can compress that really, really well. If it's a bunch of different random data, like random bits, then that won't compress as well. Right? If you try to take a movie file and run it through zip, it's not going to compress it at all, or barely, right? And then as I said before, the data system can't derive any meaning about what's actually in the data, ignoring the mod log piece, because it doesn't understand what the compression algorithm did to the data, right? If I run Snappy or ZStandard, they're doing some variant of dictionary encoding, but the data system doesn't know how to interpret what the dictionary encoding, the dictionary that was generated by that compression algorithm. Right? It's considered an opaque box. So again, as I said before, what we really want to be able to do is have the data system operate directly on compressed data without decompressing it, because it's in charge of the compressing it, and it knows how to compress it, and knows how to extract information that it needs in some cases. All right, so I say it's a real simple table. It has a name and a salary. I run it through some compression algorithm, not saying what it is, right? But say it's some variant of dictionary compression, and I've converted all the names into and the salaries into simple 2-character strings. So if my query shows up, select star from users where name equals Andy, ignoring indexes, right? Just assume I have to do a sequential scan. I do some kind of database magic, I'm not saying what it is yet, and I convert the input string to Andy into the same code that I used to represent it here. And then now my query is basically doing a name lookup where a query where name equals XX. And I know XX corresponds to Andy because I did that mapping, and I can go find exactly the data that I need. So I didn't have to decompress these other tuples to find my match. I just operated the query directly on the compressed data. So this is what we're going to want to do in a column store system if we control everything, if we control how things are being compressed and not let some third-party library do it for us. But this is only going to work, again, at the column level because now we're going to have all the values for a given attribute are just one after another, which are typically always going to be in the same domain. All right, JSON breaks all that, but we can ignore that. All right, so I'm going to do a quick run-through of the most common compression schemes. And they might have slightly different names. I'll try to cover them. For different systems, might call them different things. But these are all going to be column-oriented compression schemes that the data system can employ and be aware of in its execution engine when it runs queries to know how to access the data without decompressing it. So again, some of these you might have covered in other classes, but we'll see how we can do this in the context of databases. So one of the common ones is called run length encoding. And the idea here is that if we see the same value repeated one after another in a column, instead of just repeating that value over and over again, we'll just store the value once, store what offset we are within our column, and then store the number of times that value appears. Right? We basically convert it to a triplet. We can get a huge win for this if we sort a table based on the column we want. If the table is sorted based on the column we want to do run length encoding on, because now we could have all the values that are with this, all the tuples of the same value will appear in the same location. Sorting is kind of tricky because again, now I need to make sure that my offsets all match. So if I sort my table, I have two columns. I have to sort it the first column, and then come up with the new offsets, and then I have to make sure that the second column, those offsets get moved around as well. So what might be the best sorting? What might be the best way to get the best compression scheme is to sort this column first. Might actually be the worst way for sorting the other column. So database systems have ways to try to figure out how to sort things the best, but we'll ignore that. So say a real simple table has 8 tuples. It has some ID, like a person ID or something, and then there's a flag that says whether someone's dead or not. Right? We're ignoring nulls. You're either dead or not dead, yes or no. Right? But you can see here that it's intermixed with the different values. So in some cases, I do have some repetition. So I'll just convert those into what the value was, what the offset is, and what the length is. Right? In this case here, it's yes or no. It's Boolean, 0, 1. If I have larger values, I can basically store that as an enum, say, and just map them to 0, 1, so that in my RLE encoded pieces, or the triplets, I'm just storing what the enum value is. But for simplicity, you can ignore that. Right? So in this case here, we're actually not getting a huge win because these triplets are actually larger than what the original data was because, again, as I said, they're intermixed. But now for a query like this, like count the number of people that are dead and group by whether they're dead or not, I can just rip through the compressed data and just count up the number of times the repeated values, and that'll produce my answer real quickly. I can get better compression, though, if I sort it. Right? Because that'll avoid these issues where like it flips back from the not dead, dead, not dead. If I sort them, then all the dead people go first, followed by the non-dead people. And then now my compressed data only has 2 entries, 2 triplets of just the dead people and the not dead people, and then the number of times they each appear. So think of like, again, in other columns, like keeping track of the sex of people, right? It's a small number of values. If I sort based on that, then I could represent 1 billion people with just a small number of triplets. That's a huge reduction in size. And we'll see how RLE can be used in other compression schemes. Like you compress data once, and then you compress it again with RLE, and you get even bigger win. The next compression scheme is called bit packing. Sometimes I think it's called bit shaving sometimes in our systems. But the basic idea here is that if you recognize that all the values within a column are much smaller than what the max value could actually be, then you don't need to store a bunch of bits for unused data within each value. This is very common, right? So people would say, when you declare your table, I have these attributes I define it as an int. Well, that's a 4-byte integer. But if all my values are less than 16 bits, I don't need to store all those extra empty bits because they're nothing but a bunch of zeros. right? So say a bunch of values like this. Again, it's a 32-bit integer, but all the values are really, really small, less than 200. Then the total size is 256 bits, but all this data here I don't need. So if I can recognize this, then I do bit packing, where I just store the significant bits that actually matter, that distinguish one value to the next, and I compress it down significantly. So I went from 256 bits to 64 bits to store this data. And you just do bit shifting to put it back into the right form when it comes time to do whatever operation you need. Yes?
Sorry, going back to the previous Rollins encoding, if we store different columns, like assuming it's a columnar store and we store different columns differently, does that mean that if we want to get like one row, specifically like one tuple, we have to go scan ID completely because they're sorted differently?
Right. So the question is, if I'm doing RLE, for example, on different columns, then how do I stitch the original tuple back together? You'd have to go through and use the triplet to decide, okay, if I materialize this, if I expanded it out, the tuple I want would be at what offset? You basically, again, I'm treating the RLE as a log to say, here's going to go back to the original form. But you want to avoid having to, again, materialize all of the empty extra bits unnecessarily. Okay. The next scheme is, one problem with the bit packing is that you can have outliers. And so you have to use a technique called patching. In Amazon Redshift, they call this mostly encoding. It's basically bit packing, but when you recognize there's some tuples that have a value that doesn't fit in your bit pack version, you basically put a little marker in it, and like a special bit sequence, and say, okay, well the value for this tuple at this offset, it's actually not really here. You got to go jump to this auxiliary table to go find it. So you could rip through the column, do your processing, ignore any of the outlier values, and then just go back and get the original value that you need, the larger value. So you still get the win of bit packing, but you can handle the outliers. So in this example here, again, the original data was 256 bits, but with the bit pack scheme plus the table to keep track of the outlier, it's 112 bits. I'm showing toy examples here, but again, think in terms of billions of tuples. Next technique is to do bitmap encoding. And the idea here is that instead of storing the values over and over again within a column, I'll maintain a separate bitmap for each possible value that could occur, and just have a 1 or a 0 based on whether that tuple at that offset is set to that particular value. Right? So again, if I have the isDead column here, that instead of storing, again, yes, no over and over again, I can just have a bitmap for all the yeses, a bitmap for all the nos, and then I just know how to jump to the offset that I want to determine what the actual value is. Right? So again, the original data was 64 bits, but with the bitmap, we can get it down to 16 bits. When does this not work? When the cardinality is high. If I have a lot of values, then I have a lot of bitmaps, right? So if you look at a toy example, like I have a table of customers, and there's a zip code attribute. There's about 43,000 zip codes in the United States. So if I'm using bitmap encoding, I would have to have a separate bitmap for every single possible zip code. And if I have 10 million tuples, then those bitmaps are going to be 10 million. You have 10 million bits in them. So the original data just to store 10 million 32-bit integers is 40 megabytes, but to store 43,000 bitmaps for 10 million entries is 53 gigabytes. So in some cases, this actually would be a terrible idea, right? The other problem with bitmap encoding too is every time I insert a new tuple, I got to make sure that I append it to the end. Otherwise, I have to go, inject it in the middle and then move all the bits down, and that could be expensive. Now, this is a gross generalization. No system should not store bitmaps in this way, just raw bits. There's actually compressed bitmaps that are really useful for sparse data sets, and the most popular one is called roaring bitmaps. And it's basically like you only expand out the bitmap and have the true bits, or keep track of the bits for when you have a lot of data within a region. Right? So you're like sort of doing lazy expansion of the bitmap. But running bitmaps are used in on a lot of systems in today, and it's actually going to be used in Pino, which is what StarTree is going to be based on. We'll talk about in a second. All right, let me get through these last ones to make sure you understand that, and then I want to talk about dictionary encoding as the most important one. Delta encoding is basically keeping track of some starting point and identifying that all the values that appear after that one particular value are just small increments or decrements of that. So instead of storing the absolute values over and over again, I just say how much am I different from the one value that appeared before me or some starting point. So if I'm keeping track of temperatures at different times, at different minute offsets, right, the time's always going to increment by 1 minute, and then the temperature is not going to wildly fluctuate massively within 1 minute, right? It's not going to go from 99 degrees to 0 degrees in a minute, at least in most cases. So in this case here, I use this as my starting point, the first entry, and then all the data that comes after it are just plus or minus from the previous value, right? So I can compress this even further with RLE because what do I have here? I have a bunch of plus ones repeated over and over again, right? So I can take this column after I've delta encoded it and then just run RLE on it and compress it even further. And the data system keeps track of this all for you underneath the covers to recognize I know what the encoding scheme is for this data and how to unpack it if need be. So in this example here, again, I went from 320 bits for the original data, just for this column here, down to 96 bits. So in this example here, the delta encoding is always mean that the increment from the previous entry. There's another technique that's similar called frame of reference encoding. It's basically saying that there's some global value that I have within the column, and then all the values within the column are the delta from that. So my point here is like it's the starting point, and then everyone's a delta from before, but I could use this as the starting point, and then this would be plus 1, plus 2, plus 3, plus 4, right? But it's the same basic idea. All right, the last one real quickly is dictionary encoding. I probably should start with this first because it's the most common one. But most of you should have encountered this in other CS classes. But the basic idea here is I want to replace frequently occurring values with some integer code that I can use to represent it, and I'll have maintain this dictionary, this mapping table that says for that dictionary code, here's what the original value is. In most systems, actually nearly all systems, it's going to be a single attribute will have a single value, meaning they don't look at if I have value A followed by value B in two contiguous tuples, I can convert that to a single dictionary code to represent those two tuples. It's usually going to be one code maps to one value. And we need a dictionary scheme that can decode and encode quickly for us. And ideally, we want to expose that to the rest of the system so that for some queries, we can operate directly on the dictionary and never have to actually even look at the compressed data. So let's say we have a simple table with a bunch of names. Again, all we're going to do is replace these variable length data in this field here, in this column, with these dictionary codes. And in this case here, I've also sorted the dictionary based on the values for themselves. So now the values are going to have the same lexicographical ordering as the dictionary codes have the same lexicographic ordering as the original data. And the reason why I want to do this, because there's a bunch of tricks I can do to run queries more efficiently. If I know that Andy appears before Jignesh, therefore I would know that the value of Andy, the dictionary code Andy 20 should appear before 30. So I, again, don't have to go back and decompress things in order to figure out what's going on. So for queries like this, select star from table where name like A and D. Well, since to do the where clause, I'm only operating on name, ignoring the star part of it. I can just convert this into a between clause between 10 and 20, because again, my dictionary codes follow the same ordering as the original data. So now I can actually this query by just looking at the dictionary table and never actually even go back to the original data. So if I have a billion tuples but only 100 dictionary codes, and my query can be answered directly on the dictionary, I don't have to read 1 billion tuples. Yes?
Where is this dictionary actually stored?
This question is, where's the dictionary stored? It would be in the header of the pages. Or like in the case of Parquet, we saw the row groups. It goes in there. So some queries, again, you can in this case here, if I actually have to get the original value back, I gotta go on the columns. But if it's like, give me all the distinct names, in this case here, I can just do that directly on the dictionary. Yes?
we do the string matching A and D exactly matches code from 10 to 20, not like 10 to 30.
Going back here. So the question is, how do I convert this name like A and D into between 10 and 20?
Yeah, how do you like specify the range?
So the user wants to specify this. The data system is basically rewriting this for us. The way it works is that I know that this is the dictionary for this column. So let me just run the where A and D, where name like A and D, and I just go through the values here. They're in sorted order, and I stop when I find something that doesn't match. Like if I get to Jignesh, then I know that nothing after that could ever match my where clause. So now I know it should just be between 10 and 20. So I basically do a sequential scan of the dictionary, find the matches for my starting point and then my end point. And because it's sorted, we can exploit that. OK, to finish up. All right, the main takeaway from this class should be there's this distinction and there's pros and cons between a row store and column stores. And that if you're doing analytical system, you basically want to be in a column store, but it's typically going to be stored under the PAX model. In the early 2000s, mid 2000s, there were people who try to contort row store systems into column stores and do a bunch of store extra data structures to try to make it look like a column store. But at the end of the day, like all that went away, and everybody wants to do. You want a system that operates directly on columnar data. And we saw that because we're storing things in columns, all the values are going to be the same, or the domain is going to be much smaller for a single column than intermixing rows. That there's a bunch of compression schemes we can do to improve the storage size, improve query performance, and in some cases we don't have to decompress things to answer queries. All right, so this finishes off the lecture for the for storage, how to represent things on disk. When we start now on Monday next week, we'll then talk about, OK, when I have these pages in disk, I bring in the memory. What does that look like? How do I manage that? And how do I control that? Again, and that's what Project 1 will be based on. OK?
My name is Xiang. I'm a PMC and committer of Apache Pino project, as well as co-founder of StarTree, which is like the company trying to wrap up Apache Pino for a SaaS solution. So for this talk, I'm just trying to start with like all the Apache Pino like technical things and why we build it and some just like high level architecture kind of things. So share, not really share. I should. Yeah. Okay. So for this talk, I'm just talking about those three things. So first thing is like what we're doing is we're doing the real-time OLAP. So real-time so OLAP is for online analytics platform. It's not really like the traditional transactional databases. It's more on the analytical workload. So the differences here is like for all the queries, what we want to solve is like for a big kind of data scanning, and your query is always like probably touch every row of your database. That's the typical workload for analytical things. That is very different from the workload or the query pattern of the transactional databases. So here we are having some use cases like user-facing analytics at LinkedIn. For example, if you open LinkedIn, you will see this who viewed my profile, and all those things are being like computed for like all your viewing history for like past like a couple months, all those kind of things. So all those kind of queries are like serving directly from Apache Pino, and we're also trying to like keep up all the freshness data. Similarly, we will get use cases like okay, so one more thing was mentioning here is like the query QPS is actually very high. We're serving like more than 10,000 queries per second, and we also want to ensure the latency is very minimal. It's like P99 latency is like smaller than 100 milliseconds, which means that you can actually query the database at the when you open the or browser your profile. So another use case is like for Uber Eats, right? So whenever you order something, we want to quickly show the restaurant owners that, okay, your revenue goes up. And also here is like within your delivery kind of radius, here is like all the performance of like traffic, how people are ordering, the supply demand, all those kind of numbers. So Uber is like very sensitive to their data freshness. So we tend to like provide like a super tight kind of ingestion for them to ensure everything is up to date. Another use cases here is like for all the business metrics and anomaly detection use cases. This is like for like companies like doing business metrics and trying to analyze their business performance. And meanwhile, they want to debug, or if something goes wrong, they want to figuring out why something goes wrong, and they also want to root cause their issues. The last one is for like all those kind of like internal dashboard, right? So everyone want to know like how is my business, or how are any of those numbers means, right? So they need a lot of this kind of like a data visualization, and you have like analytical databases which is powering all those kind of dashboard. So why real time, right? So this is because of like from the industry perspective, the value of the data is actually is like more or less about like if you have a lot of data, then you do aggregation, you do machine learning, you can actually drill down a lot of like what are the pattern of the data. That kind of value is like super valuable to like business owners, and also people try to figuring out the user behaviors. But meanwhile, there will also be like for individual events, the value is like decreasing based on the time that has been vanished, right? So think of like if there's a fraud detection, someone like just swap their credit card, you want bank to like immediately detect that instead of like telling you something goes wrong like in a day or two, right? So this kind of things is like single events as soon as possible. That's the value. And for aggregate events, as much as the data you have, you get a lot of value. So that's kind of like we see the industry trend for like analytical workload. People are trying to like pushing more real-time data into for analytics, and also like people tend to like putting the analytical workload and also present all those things to the users. We call it like user-facing analytics. It means that we are actually use users' data as a product to fit into like the applications, right? So now you can see like every application is very smart. It's or like training based on your user behavior and your like user events. So this is like just don't look at it. This is like just a use case requirements which try to demonstrate that people are trying to more on the data freshness, and the query throughput is like very important once this is like user facing. Once you want more user to use the application or try to like use the database, then you actually tend to have like hundreds, thousands, or even millions kind of queries per second. That's kind of the level of the workload that we are dealing with. So what is Apache Pino? What we are building is like the fastest real-time OLAP databases, which tend to provide like very high throughput and extremely low latency, and very high like concurrency queries for the industry. So here are like a different industry like users that are powered by Apache Pino. You can see it's spread from like retailer, banking, cloud, SaaS, or food logistics. Okay, now I'm going to give a very high level architecture. So in terms of like the Pino things, so we are splitting Pino into like real-time server and offline server. This is like where we keep all the data. And then we have like a deep store, we call it the segment store. Usually we use cloud things, for example, like S3 to back up all the data. And then we have something called the controller, which internally is for like all the cluster management as well as the data management. So providing all the REST API for all the management costs. For the real-time data, it's coming from, for example, Kafka or Kinesis, those kind of the real-time data source. And then we can quickly write data into the real-time server and indexing it. And meanwhile, we will persist the data to the deep store as well. From the batch or the offline kind of servers, they are serving like more like long tail persisted data, and all those data will be like computed or ingested through something called a minion, which is kind of like the workload. The processor kind of workload thing. It's you can think of this as like similar to like Spark or Hadoop, this kind of workers that can do more things like indexing, build the pre-aggregates, all those kind of things that happening there. So this is kind of like how we are keep all the data passes, and then we have something called the Pino broker, which is going to handle all the queries. So this is like pretty much like all the deployment looks like. So from the table and the data perspective, what we're doing is like we're splitting one table into many data trunks, which we call as Pino data segments. Data segments is nothing but just like a group of the columns that has been placed, and that's kind of like your data. And but meanwhile, we're going to add like a lot of index, which is going to speed up the queries. This is kind of like the philosophy, the engineering philosophy that Apache Pino project is working on. Is trying to adopt is like we want to work smart. It's unlike like the traditional analytical kind of engine working on like, okay, I want to scanning things super fast. We are also working on like a lot of indexing, trying to say, okay, how we can try to minimize the data scanning and try to either like find out, okay, here are the data trunks with the data, are the data that you have to scan, or we can actually do a lot of things like pre-aggregates, which will for the very frequent query, you actually don't need to compute things like again, right? So this is like how we can make the database, the query engine more smart, and then it will help in terms of like getting way higher throughput, and also like once the data source, the data size is growing, you will also get like a very good performance. So this is kind of like the different kind of indexing types. We have like inverting index, sorting index, range index, also things like for geospatial kind of things. So we also do like indexing so that you don't really need to calculate latitude, longitude for all the queries, but something like if you draw a polygon, we actually know like a lot of things. Here are the points already inside it. And one more thing here we want to like emphasize is like the trade-off of the StarTree index, which is like something very unique to Pino. Internally, we're building something like pre-aggregates, right? So think of like you have some you have of course like sum, group by, those kind of things. You can either do it in key value store basis. It's like, okay, I compute all the, let's say, country equals US and browser equals Chrome, and I compute all the sum numbers. And that would be like the key value kind of lookup. That's what we call it as like a materialized view or your pre-aggregates. So in terms of like the algorithm complexity, it's like O1, right? You just do a lookup. But let's say if you just have a raw table, then you want to compute this, you actually need to scan the entire table and then to compute this number, right? So it means that your latency is very high, but you don't need to keep all the detailed numbers. So you can actually do a trade-off. So traditionally, if you want to use materialized view, it's like one or nothing, right? But we built something called the StarTree index, which allows you to actually do the trade-off based on like your storage requirement. You can actually achieve some lower latency with a certain number of the space usage. This is some like you can actually be at any point of this sliding lines. So with this kind of things, so we actually, for example, for the LinkedIn who view and profile use cases, it was actually built on this materialized view with a key value store. To serving the 1,000 cores per second, we were actually on like 1,000 machines to solve that. But once we have Pino, we can actually serve like 5,000 cores per second with only 75 same type of the machine. So this is like the engineering kind of architecturing, what we are doing is like we have a database. We also want to ensure this thing is very easy to pluggable, and also like very easy to be like extensible to like other systems or for contributors to write their own code. So we make this kind of pluggable architecture. So if you look at here, like we have multiple like SPIs in terms of like you have Pino segment SPI, which means that you can plug in your own kind of data structure or storage format. And then you have a Pino query SPI, meaning that you can have your own kind of implementation of your query engine if you want. This is something that we are building recently. We call it multi-stage query engine. It's like to support the different types of the joins. And but since Pino is like a super fast kind of query engine, we actually do a lot of heuristics, especially for like data, especially for the joining use cases. We try to like collocate the data so that from the join perspective, you don't have to like do any do much like a cross node kind of exchange, but a lot of things can just happen locally.
Xing, I gotta cut you off.
Okay,
We're out of
sure.
time. All right, we have time for one
Yeah.
question. So he forgot to mention that Pino, which started at LinkedIn, like there's something we built internally to again, do user-facing analytics. LinkedIn actually built a lot of interesting systems. Kafka came out of LinkedIn, right?
Yes.
And then became Confluent. And then Pino is sort of the other more famous one that came out of LinkedIn as well. So let's give him a round of applause. Thank you. And yes, and so the Niha and Jackie are coming next week, and so that'd be Monday and Tuesday. So please stop by and talk to them. Okay. All right, Xing. Thank you. What's that? I mean, yeah, we can post the slides. Yes. Okay. All right. All right, guys. Have a good weekend, and I'll see everyone on Monday. Okay.
I need something refreshing when I get finished manifesting. Too cold, a whole bowl like Smith & Wesson. One quart and my thoughts hip-hop related. Write a rhyme and my pen's intoxicated. Lyrics are quicker with a sip of more liquor. Since I'm a city slicker, brain waves are quicker. Rhymes I create rotate at a rate too quick to duplicate. Feel a breeze at a skate. Mics at Fahrenheit when I hold it real tight. Then I'm in flight, then we ignite. Blood starts to boil. I heat up the party for you. Let my girl rub me and my mic down with oil. Record still turns with third-degree burn for one man. I heat up your brain, give it a suntan. So just cool, let the temperature rise. To cool it off with St. Ides.